All we're going to do in this class is have a look at some special subspaces of Euclidean vectors that are associated with any matrix. Now that looks like a very limited program, but on the other hand, I'm sure you're not going to be too upset about the fact that one class doesn't seem to have a lot into it. But on the other hand, it is actually not such a limited program for two reasons. First of all, it will give us an opportunity to have a look at some subspaces, so reinforcing our understanding of subspaces and seeing what happens in how they work out, what they look like, and how to find their basis and so on in a very concrete case. On the other hand, it will actually lead directly to what is one of the most important theorems of linear algebra, and hopefully you're going to find this theorem, or this first introduction to this theorem, rather painless. Not that the theorem itself is painful, but it is a very important theorem. We're going to see it again in a more abstract situation. Remember, we're going to look only at Euclidean vectors here, but we're going to be looking at this same theory in a more abstract situation later on. So this is going to be a good way to review and reinforce certain ideas, as well as good preparation for what is coming next. So from now on, we're going to consider a matrix A like the one you see in front of you. We're going to keep that in front of us all the time, and we're going to see what we're going to do with it. The first special subspace we're going to look at is something called the row space of a matrix, and as you can imagine, it has something to do with the rows of a matrix. More in particular, given a matrix A, we're going to write this matrix as a bunch of rows. So think of that matrix we're given up there as a set of rows, row 1, row 2, row m. So what we're going to do is we're going to look at the span of those rows. So we're going to think of those rows as Euclidean vectors. We're going to consider all linear combinations, and we're going to call this thing the row space of A, denoted row A, for obvious reasons. What we want to do is gain a better understanding of what this row space consists of, what it is made of, and in particular, what we are aiming for is finding a basis for it. Alright, one thing to consider is the fact that when we do row operation in a matrix, those row operations only involve linear combinations. And what that means is that whenever we do row operations, we're not changing the row space. We're just moving from one vector, from one row vector to a different row vector, which is a linear combination of the previous ones. Therefore, it is in the same space. And what that means, therefore, is that the row space of a matrix is the same as the row space of its REF. Doing REF only involves linear combinations. Switching rows, of course, does not change the span. Adding to a row multiple on another row just changes which vectors we're using, but not the set of linear combinations. And multiplying a row by a non-zero scalar, of course, again, does not change the vectors we're using. Alright, so what we can do in order to analyze the row space of a matrix is, first of all, we can move on to the row space of its REF. What's the advantage of it? Well, as we've seen before, or as we know from the beginning, the non-zero rows of the REF have to be linearly independent, right? Because if they were not, then we would be able to eliminate one of them. And therefore, that means that the non-zero rows of the REF of the matrix form a basis for the row space of A. So that tells us a very simple way of figuring out what is a basis for the row space of a matrix. Just put it in REF form and look at its non-zero rows. This is something we've done very many times before, and that we will do again for other purposes. And so we're going to use this particular technique to find a basis for the row space. How about columns? Well, we can play the same game with the columns of a matrix. So, given a matrix, we can think of this matrix as being made up of columns. So, think of it as a set of columns, C1, C2, Cn. And as before, what we're going to do is we're going to look at the span of these columns. So, what subspace is obtained by considering all linear combinations of the columns of the matrix. Okay, so this is what we're going to call the column space of A. Now, since we are now dealing with the columns of A, doing row operations And that can be a little bit of a problem because, of course, row operations are going to affect only some of the components of the columns but not others, so we're not quite sure exactly what is going to happen to those columns. Now, we do have one way to approach the problem, and namely noticing that the column space of A is just the row space of the transpose, right? So one thing we can do is we can obtain a basis for the column space of A by computing the REF of A transpose and then figuring out from it what the the non-zero rows are, and so they're going to form a basis for the column space of A. So in other words, we have to start from A, transpose it, get the REF, read the non-zero rows, transpose them again, and now we're finding the basis for the column space of A. Okay, but given that in order to get a basis for the row space of A, we had to compute the REF of A. Well, maybe we have already computed the REF of A. Do we really want to go back and compute the REF of A transpose? Or is there a way that we can find what the basis for the column space of A is straight from the REF of A? Believe it or not, there is one, and here it is. So as I said, doing row operations changes columns, and it changes those columns to vectors which are likely to be outside of the column space of A. We're changing only some components but not all of them, not through linear combinations. So we're going to look at it from a different angle. Think of the homogeneous system AX equals 0. Okay? Now this system is equivalent to the system obtained by considering the REF of A times x equals 0. Remember, that's one way to solve, or that's not one way, it's the way to solve any linear system, right? We start from A, compute its REF, and then read off the solution from that one. Okay, so what that means is that if we look at the system written this way, now notice that this equation looks like a simple equation, but it's really a matrix equation still, or actually it's a vector equation. On the left hand side we have all the columns of A, each one of them multiplied by the corresponding variable. On the right hand side we have the vector 0. Well, this equation will have exactly the same solutions as the equation obtained by considering the columns of the REF. What does that mean? It means that even though the columns are different, but their mutual relationship in terms of dependence or independence is going to be the same. So in other words, the columns of A are linearly independent, or certain columns of A are linearly independent if and only if the corresponding columns of the REF of A are linearly independent. Okay. Now, this may look like a little bit of a deep concept that you may want to stop, rewind, and listen to it again, but I'm going to repeat it for your convenience. So even though the columns are going to be in a different subspace, and therefore we cannot really work on the columns of the REF to find a basis for the column space, but the linear independence relationship is going to be the same. So if we get a set of columns in A, so if we get a set of So if we have a set of columns of A which have a certain, so up here, this column and this column, say, and some other column, which have a certain linear relationship, well, the same relationship will occur around here, because these two equations are going to have exactly the same set of solutions. So if there is a set of solutions with non-zero numbers x1, x2, etc. in one set, is going to be the same as the other one. And this implies again that certain columns of A are going to be linearly independent or linearly dependent if and only if the corresponding columns of the REF are linearly independent. And that gives us a way of finding a basis for it. Okay? And the way goes as follows.